Welcome to another podcast from the Rooster Podlog. Today, we're diving deep into Apache Iceberg, a technology that's really shaking up how organizations handle and analyze their massive data sets.
Yeah, it really is.
Think of this as your direct line to understanding Iceberg without getting lost in, all the technical weeds.
Exactly. Our goal in this deep dive is to explore the core ideas behind Iceberg, its fundamental structure, and how it manages data, both when it's actively being processed and when it's just sitting there at rest. We'll also touch on keeping this data secure and what's involved in moving to this, more modern approach. We're drawing on detailed notes to give you a comprehensive understanding of what makes Iceberg tick and why it's such a powerful tool.
Right. Consider this your personalized roadmap to unlocking the potential of Iceberg.
Yeah.
Okay, let's get right into it.
Let's do it.
We're going to start by looking at how data architecture has evolved. That's pretty fascinating to see the journey, isn't it?
It really is.
We began with OLTP systems, that's online transaction processing, which were fantastic for handling day-to-day operations. Imagine a drone manufacturing company taking individual customer orders.
Right, simple transactions.
Yeah, you could have a simple Python script using something like psycopd2 to instantly record each new order in your database. Dead simple.
Precisely. OLTP systems are the backbone for those immediate transactional needs. They excel at those quick, single-record operations required for things like order entry or managing your inventory levels. But here's the thing. The moment that drone manufacturer wants to step back and look at the bigger picture, say, analyze their total profits over the last quarter, broken down by drone model and sales region.
Yeah, the analysis part.
Those same OLTP systems start to struggle. They weren't really built for that kind of broad analytical querying.
Right. They're just not designed for that heavy analytical lifting. That's where OLTP online analytical processing comes into play, often using dedicated data warehouses. But even with these powerful data warehouses, we started running into some, limitations.
Yeah, definitely. What's really interesting is that while data warehouses provided a centralized place for analysis and historical insights, they often came with certain trade-offs.
Like what?
Well, think about getting locked into a specific vendor because they use proprietary data formats. That limits your flexibility down the line, you know?
Oh yeah, vendor lock-in. Big one.
Huge. Then there's the cost. Storing and processing massive amounts of data in these systems can become very expensive very quickly. Plus, they weren't initially designed to handle the variety of data we see today, like unstructured data from drone cameras, perhaps.
Right, images, video.
Exactly. And they weren't always the best fit for the intensive computations involved in machine learning. So if you wanted to apply AI to your drone performance data, it might not have been the ideal environment.
Okay. So to address those kinds of issues, we saw the rise of data lakes. The idea was to create this huge, flexible storage space where you could throw all your data, no matter its structure, at a much lower cost, typically using open formats.
Right. Think Hadoop, HDFS, and then later cloud object storage like S3.
Exactly. We saw companies adopting the Hadoop ecosystem and then moving to cloud-based object storage. Imagine a PySpark script pulling in all sorts of raw drone quality inspection data from the data lake, maybe CSV files, JSON logs, even those drone images, and doing some initial analysis on things like defect rates per component or across different manufacturing plants.
Yeah, and connecting this to the bigger picture, data lakes offered that crucial agility and cost effectiveness, and they were definitely better suited for handling diverse data types and for machine learning initiatives.
Oh, there's always a but.
There is. They also brought their own set of challenges. Performance could be, unpredictable because of the sheer volume and variety of data. Configuration could become quite complex as you tried to organize and manage everything.
Right, the data swamp problem.
Kinda, yeah. And perhaps most importantly, they often lacked the strong ACID transaction guarantees that data warehouses provided. This meant ensuring data consistency and reliability could be a real headache. Imagine trying to track drone component failures and having inconsistent records that could have serious implications, right?
Definitely. And that, in a nutshell, brings us to the data lakehouse. It's like someone said, why can't we have the best of both worlds?
Exactly.
The goal is to combine the speed and governance of a data warehouse with the flexibility and lower cost of a data lake. And technologies like Apache Iceberg are absolutely key to making this vision a reality.
And what's truly transformative about the data lakehouse paradigm and what Iceberg enables is how it directly tackles those earlier limitations.
How so?
Well, we're talking about significantly fewer copies of your data, which immediately reduces redundancy and, the potential for discrepancies.
Right.
Then you have much faster query performance, thanks to how Iceberg manages its metadata. We'll get into that.
Right.
The ability to easily go back in time with historical snapshots provides a crucial safety net and opens up possibilities for audit and compliance.
Ah, time travel. Very cool.
Super useful. Plus, the overall architecture is more cost-effective, and the commitment to open standards means you avoid getting locked into proprietary systems.
Yeah, that open standards part is big.
It is. Think about a PySpark example creating an actual Iceberg table to store your drone assembly metrics suddenly. That data is under a much more organized, reliable, and performant management layer.
Now, we've been throwing around the term table formats. For someone listening, what exactly is a table format and why should they even care about it?
That's a really important question to clarify. A table format, at its core, defines how data is organized and managed within a data storage system. It's the layer that sits between your actual data files and the tools you use to access and analyze that data.
Okay, the intermediary.
Kind of, yeah. It handles crucial aspects like defining the structure or schema of your data, managing updates and deletions, ensuring consistency, and optimizing how data is read and written. Without a well-defined table format, you're essentially dealing with a chaotic collection of files, making it incredibly difficult to reliably query, manage, and trust your data. It's like trying to find a specific book in a giant, unorganized pile versus looking it up in a library catalog.
That makes perfect sense. So before Iceberg came along, what was the sort of foundational table format in the data lake world?
That would be Apache Hive. Developed at Facebook, Hive was really the pioneering table format for data lakes.
Right, I remember Hive.
Essentially, Hive treats all the files within a specified directory, or a set of directories, as a single table. It uses subdirectories to manage partitioning and relies on a separate service called the Hive Metastore to keep track of the location of your data files and the schema of your tables.
But as we touched on earlier when we were talking about the challenges of data lakes, Hive had its fair share of limitations, right?
Absolutely. While Hive was groundbreaking for its time, its directory-based approach had several inherent drawbacks. For one, performing operations at the individual file level could be quite inefficient, especially when dealing with a massive number of small files.
Small file problem.
Exactly. It also lacked true atomicity across multiple partitions, meaning if you were updating data that spans several partitions, the operation could potentially fail partway through, leaving your data in an inconsistent state.
Ouch.
Yeah, not good. Concurrency control was also limited, making it difficult for multiple users or processes to safely write to the same table simultaneously. Listing all the files within very large directories could be incredibly slow, impacting query planning.
Right, just listing files takes forever sometimes.
Tell me about it. And finally, users always had to be explicitly aware of how their data was partitioned when writing queries, which wasn't always user-friendly and could lead to errors if not done correctly.
That really paints a picture of why a more robust solution was needed. And that solution, at least in part, is Apache Iceberg. Can you tell us a bit about where Iceberg originated and what the main design goals were?
Yeah, it's a fascinating story, actually. Iceberg was born out of necessity at Netflix back in 2017.
Netflix, okay.
Yeah, they were grappling with massive petabyte-scale data sets in their data lake and were hitting all the limitations we just discussed with Hive, but on a much, much larger scale.
Wow.
So they decided to build a new table format from the ground up to specifically address these pain points. In 2018, they recognized the broader need for such technology and open-sourced it to the Apache Software Foundation.
Smart move.
Definitely. The key design goals for Iceberg were to provide strong consistency through ACID transactions, deliver much better query performance by leveraging sophisticated metadata management, offer ease of use by abstracting away the complexities of partitioning.
That's a big one.
Huge. Enable safe and flexible evolution of table schemas and partitioning strategies, and of course, be able to scale reliably to those massive petabyte-level data sets that companies like Netflix were dealing with.
Petabyte scale. That's almost hard to even imagine. And Iceberg has some pretty impressive features that help it achieve those goals, right?
It certainly does. Let's highlight some of the key capabilities. First and foremost, you have AC transactions, which, as we briefly mentioned, guarantee that write operations are atomic, all or nothing, consistent, data remains valid, isolated, concurrent operations don't interfere, and durable, changes stick.
The EC guarantees, yeah.
Yeah.
Critical.
Absolutely. Then there's partition evolution, which allows you to change how your data is organized into partitions without having to rewrite all your existing data.
That's flexible.
Very. Hidden partitioning is a real game changer for usability. You can partition your data based on transformations of your natural data columns, like extracting the day or month from a timestamp, but users can still query using the original timestamp column without needing to know about the underlying partitioning scheme.
Ah, so it hides the complexity. Nice.
Exactly. Iceberg also supports row-level operations, offering both copy-on-write and merge-on-read strategies for handling updates and deletes efficiently.
I'll probably dig into those later.
We will. Time travel is another incredibly useful feature, allowing you to query past versions of your data as if you were going back in time.
Like version control for data.
Pretty much.
That's
This naturally leads to the ability to perform version rollback if something goes wrong. And finally, Iceberg provides robust schema evolution, so you can add, rename, or change columns in your tables without breaking existing queries or requiring massive data migrations.
schema evolution without breaking things. That's huge.
It is. And we can even picture some Iceberg examples for these, like adding a new assembly notes column to our drone metrics table, simple metadata change in Iceberg, or using time travel to compare drone flight performance from last week to today, or using merge on red to efficiently update the status of drones post-inspection. It makes these common tasks much smoother.
Okay, so Iceberg sounds like a significant leap forward. Now, let's delve into how it actually works under the hood. I understand it's built on a 3-layer architecture.
That's correct. Iceberg's architecture is thoughtfully designed with a clear separation of concerns, and it revolves around 3 fundamental layers: the data layer, the metadata layer, and the catalog layer.
Okay, 3 layers.
And this 3-tiered structure is really what enables Iceberg to overcome many of the limitations we saw with earlier data lake table formats like Hive.
Let's start by exploring the data layer. What's happening at this level?
So the data layer is where the actual content of your Iceberg tables is physically stored. Typically, this resides on a distributed file system like AGFS in on-premise environments, or in cloud-based object storage services such as AWS S3, Azure Data Lake Storage, ADLS, or Google Cloud Storage, GCS.
The raw files, basically.
Essentially, yes. The data itself is organized into what we call data files. Iceberg is designed to be flexible and supports various file formats for these data files, but Apache Parquet is by far the most prevalent and highly recommended, especially for analytical workloads.
Why Parquet specifically?
Well, its columnar storage format offers significant advantages for querying. It allows the engine to only read the specific columns needed for a given query, significantly reducing I/O.
Right, column pruning.
Exactly. It also enables efficient predicate pushdown, where filtering conditions are applied closer to the data source, and generally provides better compression compared to row-oriented formats like CSV.
Makes sense.
For instance, if we're storing detailed sensor readings from drone flights, using Parquet would allow us to quickly analyze just the altitude data across all flights without having to load all the other sensor readings. You could write this pretty easily with PySpark, just taking a data frame and writing it out using .write.parquet.
And you mentioned delete files earlier when we were discussing features. Where do those fit into this data layer?
Good question. Delete files are a specific type of file introduced in Iceberg version 2 and are primarily used in conjunction with tables that employ the merge-on-read or MOR update strategy.
Okay, and more specific.
Right. In AMOR tables, instead of rewriting entire data files when you need to delete or update a small number of rows, Iceberg can write these changes to separate smaller files called delete files.
Oh, like a Delta file?
Sort of, yeah. There are 2 main types: positional deletes, which identify specific rows to be deleted based on their physical location within a particular data file.
Like a row number 234 in file X.
Exactly. And equality deletes, which specify that all rows matching certain column values should be considered deleted, for example, deleting all records where the drone aid is D1002 because that particular drone was found to be defective. Again, PySpark has methods to handle these deletes against an Iceberg table configured for MRR.
Interesting. So it's like keeping track of the changes without having to immediately rewrite the entire data set. Now let's move up a level to the metadata layer. This really sounds like the intelligence center of Iceberg.
You've got it. The metadata layer is a hierarchical structure that meticulously tracks all the data files in the data layer, along with essential metadata and statistics about them. It's comprised of several key components, starting with manifest files.
Manifest files. Sorry.
Manifest files are essentially lists that record subsets of data files and potentially delete files. For each file they track, they include the file's path in the storage system, file-level statistics, such as the minimum and maximum values for key columns, and the number of null values.
Useful for querying.
Very useful. Information about how the data within the file is partitioned, and the total number of records in the file. This detailed information is absolutely critical for efficient query planning because it allows the query engine to intelligently prune or skip entire data files that are known not to contain any data relevant to the query being executed without needing to actually read the contents of those files.
So it avoids reading unnecessary data.
Precisely. You could potentially examine these manifest files, maybe using Spark to read the JSON content if you know where they are to see what they contain.
And how are these individual manifest files organized and managed at a higher level?
That's where manifest lists come into play. A manifest list serves as a pointer to a collection of manifest files that together define a complete snapshot of the table at a specific point in time.
Ah, okay. So a list of manifests makes the snapshot.
Essentially, yes. It's a list of all the relevant manifest files that constitute a particular version of your Iceberg table. Manifest lists are what enable Iceberg's time travel capabilities by allowing the system to easily identify the set of manifest files that were active at a given time.
Got it.
They also provide another layer of filtering during query planning, allowing the engine to quickly determine which manifest files even need to be examined based on metadata stored within the manifest list itself, such as the range of partition values covered by the manifests they reference. You can usually query the table's snapshot history to see these manifest lists.
Okay, so manifest lists point to sets of manifest files, which in turn describe the data files. What about the overall definition of the table itself? Where is that stored?
That's the role of the metadata files. These are the top-level files that define the fundamental characteristics of an Iceberg table. A metadata file contains critical information, such as the table's schema, the names and data types of its columns, the history of schema changes.
Ah, the evolution stuff.
Right, the specification for how the table is partitioned, the defined sort orders for data within files, a history of all the snapshots that have been taken of the table, and various table-level properties and configurations.
So the master blueprint.
Basically. And importantly, every time you make an atomic change to the table's metadata, such as adding a new column or changing the partitioning, a new metadata file is created. This creates a linear, immutable history of the table's structure and state, with each metadata file pointing to the manifest list that represents the corresponding version of the table. Again, you can often query the metadata log entries to see this history.
And you briefly mentioned puffin files earlier. How do they fit into this metadata layer?
Right, puffin files. They are a more recent and advanced addition to Iceberg's metadata capabilities. They are designed to store richer, more sophisticated statistics and even indexes that can further accelerate certain types of queries.
Like what kind of stats?
While manifest files provide basic file-level statistics, puffin files can contain things like histograms for value distributions within columns, or even probabilistic data structures like theta sketches from Apache data sketches, which allow for very efficient and accurate approximate distinct calculations on massive data sets.
Okay, so for more complex analytics.
Exactly. Think of them as an extra layer of intelligence about your data that can help the query engine make even smarter decisions about how to retrieve the information you need. Creating a table doesn't automatically mean puffin files. It usually involves specific write configurations.
Okay, so we've got the data, and we've got all this rich metadata describing the data and its history. What's the component that allows systems to actually find and access this metadata for a given table? That must be the catalog layer.
Exactly. The catalog layer acts like the central registry or phone book for your Iceberg tables. Its primary responsibility is to maintain the mapping between user-friendly table names, for example, drone catalog.production.manufacture drones, and the current location of the metadata file for that specific table in your storage system.
The pointer to the current state.
Precisely. And the catalog has some very important requirements to fulfill this role effectively. First and foremost, it must support atomic updates to these metadata pointers. This is absolutely crucial for ensuring data consistency.
Why atomic?
Because when a write operation to a table is successfully completed, the catalog must be able to instantaneously switch the pointer from the old metadata file to the new one. This prevents readers from seeing a partially updated state of the table.
Ah, consistency. Got it.
The catalog also handles namespace management, allowing you to organize your tables into databases or schemas. And some more advanced catalog implementations might even provide additional features like concurrency control to manage simultaneous read and write operations more effectively.
And as we briefly touched on before, there isn't just one way to implement this catalog layer, right? There are different types of catalogs you can use with Iceberg.
That's right. Iceberg is designed to be quite flexible and can integrate with various underlying catalog implementations. One of the simplest is the Hadoop catalog, which typically uses the underlying file system itself to store the metadata files and relies on the atomic rename operations provided by the file system to ensure consistency.
Okay, simple start.
Yeah, often good for testing or simpler setups. The Hive Metastore catalog is a very common choice, especially if you're already using Apache Hive or Spark in your data infrastructure. It leverages your existing Hive Metastore service to store the location of the Iceberg metadata files.
Makes sense if you already have Hive.
Exactly.
Yeah.
The AWS Glue catalog is a popular managed service within the Amazon Web Services ecosystem. It offers a serverless, scalable, and highly available metastore that integrates seamlessly with other AWS services like Athena and Glue ETL.
The cloud-native option for AWS.
Right. For organizations looking for more advanced data lake management capabilities, including Git-like version control for their entire data landscape, Nessie provides a powerful option. It allows for branching, tagging, and merging of your data catalog.
Ooh, Git for data. Interesting.
It is. The REST catalog offers a more decoupled approach, communicating with a dedicated catalog server over a REST API, which provides a lot of flexibility for custom backend implementations. The JDBC catalog uses a traditional relational database accessible via JDBC to store the metadata pointers. And finally, because Iceberg is an open standard, it's even possible to build your own custom catalog if you have very specific requirements. We even saw a configuration snippet earlier showing how you'd tell Spark to use the AWS Glue catalog, setting properties like the warehouse path and the specific implementation class.
That's a really comprehensive overview of the architecture. Now, let's walk through the typical life cycle of operations. Let's start with writing data. What happens when we issue a create table command for an Iceberg table?
Okay, so when you execute a create table command for an Iceberg table, the process begins with the system parsing your command to understand the intended schema of the table, any specified partitioning or sorting configurations, and other table properties.
Standard SQL parsing.
Right. Once this is understood, Iceberg initializes the table's metadata. This involves creating an initial metadata file, which contains the table's schema and other initial settings. This metadata file is then written to the designated storage location. And finally, a record of this new table and the location of its metadata file is registered in the chosen catalog.
So, create the blueprint, store it, tell the catalog where it is.
Exactly. That registration is what makes the table discoverable and accessible by its name. You could do this with a simple create table statement in Spark SQL, specifying using Iceberg and maybe some partitioning like we saw for the drone test flight data.
Okay, that seems pretty straightforward. What about when we actually insert new data into an existing Iceberg table?
The insert operation involves a more detailed sequence of steps. First, the compute engine, like Spark or Flink, consults the catalog to retrieve the current state of the table. This includes fetching the location of the most recent metadata file.
Got to know the current state first.
Right. Then, the new data that you're inserting is written out to one or more new data files in the data layer, typically in the Parquet format for efficiency.
Write the new data files.
Once these new data files have been successfully written to storage, Iceberg creates new manifest files in the metadata layer. Each of these manifest files tracks a subset of the newly written data files, recording their paths, statistics, and partition information.
Create the manifests for the new files.
Next, a new manifest list file is generated. This manifest list references the newly created manifest files along with any existing manifest files that are still part of the current table state.
Update the manifest list.
Following this, a new metadata file is created. This new metadata file points to the newly generated manifest list, effectively representing the updated state of the table, including the newly added data.
Create the new master blueprint.
And finally, the catalog is updated to point to this new metadata file. This last step is crucial as it atomically makes the newly inserted data visible to subsequent read queries.
And update the catalog pointer. Got it. So you can do this with the standard SQL insert into or using the Spark Data Frame Write API with mode append.
Precisely. Both achieve the same underlying sequence of operations.
So it's a carefully orchestrated sequence of metadata updates that ensures consistency. What about the more complex merge operation, which can handle inserts, updates, and deletes simultaneously?
Ah, merge. Yes, it's designed to perform a combination of insert, update, and delete actions on an Iceberg table in a single atomic operation.
Like in UPassert.
Exactly, or more complex conditional logic. The initial steps are similar. The compute engine queries the catalog to get the current metadata. Then, depending on whether the target table is configured to use copy on write, seek out W, or merge on read, or more for handling updates and deletes, the subsequent processing differs significantly.
CLW versus more again. How does it differ?
In TOW mode, if a row is updated, the entire data file containing that row is typically rewritten with the updated information. Similarly, deleting a row might involve rewriting the data file without that row.
So copy on write rewrites whole files.
Often, yes. In more mode, as we discussed earlier, updates and deletes are often recorded in separate delta files, including those positional and equality delete files, while new data for inserts is written to new data files.
More all uses the delete files.
Right. Regardless of whether it's COW or more, the outcome of the merge operation is a new set of data files in COW, or a combination of new data files and delta files in more that reflect the changes.
Okay.
This is followed by the creation of new manifest files to track these changes, an updated manifest list, a new metadata file pointing to the updated manifest list, and finally, an atomic update to the catalog to point to this new metadata, making the entire set of changes visible at once. Spark SQL's merge into statement handles this, letting you specify conditions for when to update, delete, or insert.
That's a good overview of write operations. Now let's switch to the other side, reading data. What happens when we execute a select query against an Iceberg table?
Okay, the life cycle of a select query begins with the parsing of the SQL query. Standard stuff.
Yep.
Following this, the query engine contacts the catalog to retrieve the location of the current metadata file for the target Iceberg table.
Get the latest blueprint location.
Right. This metadata file is then read to locate the current manifest list for the table's active snapshot. The manifest list is subsequently read to get a list of all the manifest files that are part of this snapshot.
Follow the pointers. Catalog metadata file, dat manifest list, manifest files.
Exactly. The query engine then examines these manifest files, utilizing the statistics they contain, like min-max values and null counts for columns, and the partition information, to identify the data files that might potentially contain the data that satisfies the query's filtering conditions. This process is known as file pruning.
Ah, the optimization step, using the stats.
Precisely. Only the data files that are deemed relevant after this pruning step are actually read from the data layer. The data from these files is then processed according to the query filtering, aggregations, joins, etc., and finally the results are returned to the user. So a simple select from drone flights, where data pools, would automatically benefit from partition pruning and potentially file pruning based on stats within that partition.
So all that rich metadata we talked about earlier is really crucial for optimizing which data actually needs to be accessed and processed. What about those powerful time travel queries? How do they work their magic?
Time travel queries are a really compelling feature of Iceberg, made possible by its comprehensive snapshot history. When you specify a point in time, using a timestamp with as of timestamp, or a specific snapshot ID using as of version in your query.
Like going back to last Tuesday at 5 p.m.
Exactly. Iceberg doesn't just look at the latest metadata for the table. Instead, it goes back through the chronological history of metadata files associated with that table. It finds the metadata file that was current at the specified timestamp or corresponds to the given snapshot ID.
Finds the old blueprint.
Finds the old blueprint. Once it locates this historical metadata file, the subsequent steps of query planning and execution proceed exactly as they would for a regular select query, but they operate on the table state as it existed at that specific point in the past.
So it reads the data files relevant to that old snapshot.
Correct. This allows you to perform powerful analyses like comparing data before and after a specific event, ensuring compliance by auditing historical data, debugging data inconsistencies by examining past states, and reproducing analyses with guaranteed consistency, all with minimal storage overhead, because Iceberg efficiently reuses the data files from previous snapshots that are still relevant. You could run two queries, one ASOF before change and one ASOF after, to directly compare results.
That's incredibly useful for understanding data evolution and for those what did the data look like then scenarios. Now, let's dive into making these Iceberg tables perform optimally. What are some key techniques we should be thinking about?
Optimizing Iceberg tables is essential for achieving the best query performance, especially as your data volumes grow. One of the first and most important considerations is compaction.
Right, fixing the small file problem we mentioned.
Exactly. As we touched on with streaming and frequent small writes, you can end up with a large number of small data files, which can significantly degrade query performance due to increased I/O overhead. Compaction is the process of rewriting these small files into larger, more manageable ones.
How do you do that?
Iceberg offers several strategies for compaction, often executed via procedures like rewrite data files. The bin pack strategy is the default and aims to efficiently pack smaller files together based on their size. Just make fewer, bigger files.
Okay, simple packing.
Then there's the sort strategy, which goes a step further by not only compacting files, but also sorting the data within the new, larger files based on specified columns. This can dramatically improve query performance if your queries frequently filter or join on those sorted columns.
Sort the data while compacting. Makes sense.
And finally, Zorter is a more advanced sorting technique that can be particularly beneficial when your queries involve filtering on multiple columns simultaneously, as it tries to group together rows that are similar across all the specified columns.
Z-ordering for multi-column filters.
Okay. Yeah, so you might call rewrite data files with strategy bin pack or strategy sort and specify sort columns, or strategy zorter and specify the z-order columns.
So it's not just about the size of the files, but also how the data within them is organized. What about the initial organization of the data when we first write it? How does sorting play a role there?
That's a great point. Even when initially writing data to Iceberg, you can specify a sort order for the data within the files using either the sort or sorter options, often through data frame write options or table properties.
So sort it as you write it.
Exactly. This proactive sorting can significantly improve the performance of subsequent queries that filter or join on those sorted columns, because the query engine can leverage the metadata, min-max values within the sorted ranges, to quickly skip over large sections of files that don't contain the desired data. Z-ordering, as mentioned before, is particularly effective when you have multi-dimensional filtering patterns. You might use sort by dronead component when writing your assembly data with Spark, for instance.
We also talked about partitioning earlier. How does that fit into the performance optimization picture?
Partitioning remains a crucial optimization technique in Iceberg. By dividing your table's data into separate sets of files based on the values in one or more partition columns, you enable a powerful optimization called partition pruning.
Skipping entire folders, essentially.
Pretty much. When you query data with filters on the partition columns, the query engine can completely skip reading entire partitions that don't contain any matching data. But Iceberg's hidden partitioning feature simplifies this significantly.
How so?
Instead of requiring users to explicitly create and manage partition columns, you define transformations, like extracting the year, month, or day from a natural timestamp column using functions like years, months, days that Iceberg uses to organize the data.
Ah, so you partition by days, event timestamp.
Right. But users can then query using the original event timestamp column, and Iceberg automatically figures out which partitions are relevant based on the hidden transformation. It's much more intuitive.
That does sound easier.
And furthermore, Iceberg supports partition evolution, allowing you to change your partitioning strategy over time. Say, go from daily to hourly partitioning as your data access patterns evolve without requiring a complete rewrite of your historical data.
Wow. Change partitioning without rewriting history.
Yep. It tracks the different partition specs over time.
We've talked about copy on write, COW, and merge on read and more strategies. How do those impact performance?
Right. See how W and more represent a fundamental trade-off between read and write performance for update and delete operations. Let's quickly recap.
Okay.
COW updates and deletes rewrite entire data files. This makes writes slower, but reads are faster because the data is always in consistent base files.
Yeah.
Good for read-heavy workloads.
Got it. TWE slower writes, faster reads.
And more are. Updates and deletes are lit into separate delta delete files. This makes writes faster, but reads can be potentially slower because the engine needs to merge the base files and delta files on the fly. Good for write-heavy workloads.
And more are faster writes, potentially slower reads, needs compaction.
Exactly. Choosing between COW and Mera depends heavily on your workload patterns. If your drone status table is updated very frequently with real-time information, Mera might be more suitable for its faster writes, but you'll need to compact it regularly. If you primarily read the status information and updates are less frequent, COW might offer better read performance out of the box. You can often set the mode using a table property like write.format.defaultMore.
Are there any other knobs and levers we can play with to further optimize Iceberg performance?
Absolutely. There are several other important optimization considerations. Collecting detailed metrics during write operations enhances the accuracy of file pruning. Regularly rewriting manifest files using the rewrite manifest procedure can sometimes improve query planning efficiency.
Okay.
It's crucial to manage snapshot expiration using expire snapshots to remove old snapshots and allow the underlying data files to be garbage collected, saving storage costs.
Clean up old versions.
Right. Similarly, running orphan file remove ran files, cleans up any data files that aren't linked to any valid snapshot. The write.distribution mode table property can be tuned to control how data is distributed across files during writes, maybe hash for better distribution or none for simple uptends. When using object storage, be mindful of potential request throttling and configure I/O settings. And for highly selective queries, you can consider enabling Bloom filters, which can help quickly rule out files that don't contain specific values.
Lots of tuning options there. Let's move on to the catalog layer again. We know it's essential. What are the fundamental requirements for any good Iceberg catalog implementation?
At its core, a reliable Iceberg catalog must provide a consistent and up-to-date mapping between table identifiers and the location of their current metadata. To achieve this, the most critical requirement is the ability to perform atomic updates to the metadata pointer.
That atomic pointer swap again.
Exactly. When a write operation is committed, the catalog must instantaneously and reliably update the pointer to the new metadata file. That atomicity guarantees readers always see a consistent view.
Crucial.
Beyond this, a catalog needs to effectively manage namespaces, organizing tables into databases or schemas. And for environments with multiple concurrent users, robust concurrency control mechanisms within the catalog can be highly beneficial.
We've discussed various catalog implementations. Let's briefly revisit some of the key ones and maybe touch on when you might choose a particular one.
Certainly. The Hadoop catalog is often chosen for its simplicity, maybe for development or smaller setups. The Hive Metastore catalog is a natural fit if you're already in the Hive ecosystem.
Right.
The AWS Glue catalog is popular in AWS for its serverless nature and integration. Nessie stands out when you need that Git-like versioning for the whole catalog branching, tagging across tables.
That sounds powerful for complex environments.
It really is. The REST catalog offers flexibility for custom setups. The JBBC catalog uses a relational database, which might fit well in some traditional IT environments. Ultimately, the choice depends on your infrastructure, cloud provider, management overhead tolerance, and required features. You configure Spark to use these via properties like setting the catalog impl for Glue or the URI for a REST or Nessie catalog.
And if we decide to switch our catalog implementation at some point, is that a complicated process?
Generally speaking, migrating between Iceberg catalog implementations is designed to be as seamless as possible. Because Iceberg cleanly separates the data files from the metadata, and the catalog primarily manages pointers to the metadata, you typically don't need to physically move or rewrite your data.
So just update the pointers.
Pretty much. The core of the migration involves updating the registration of your Iceberg tables to point to the new catalog. There are various tools and methods. Some engines provide utility procedures like migrate or register hateable. You might also be able to register existing Iceberg table metadata into a new catalog simply by telling the new catalog where the existing metadata file is located, maybe via an alter table statement, setting the metadata location property conceptually.
That's reassuring to know it's not a completely disruptive process. Now, one of the really interesting aspects of Iceberg is that it exposes its internal metadata as queryable tables. Why is this such a powerful feature?
Oh yeah, this is super cool. Exposing its internal workings as queryable metadata tables is a truly powerful and unique aspect of Iceberg. It provides an unprecedented level of transparency and allows you to gain deep insights into the structure, history, and even performance characteristics of your tables using standard SQL queries.
Querying the metadata itself.
Exactly. This opens up a wide range of possibilities for diagnostics, monitoring, auditing, and advanced data management tasks that would be far more complex or even impossible with traditional table formats. You can just run select from my table.history, for example.
So what are some of these key metadata tables that we can actually query?
There are several very useful ones, accessible using dot notation like mytable.files or mytable.history. The history table shows the snapshot lineage, snapshot ID, parent ID, timestamp operation, summary. Great for auditing changes.
Okay.
The metadata log entries table tracks every change to the table's main metadata, file timestamp, file path, associated snapshot ID. The snapshots table gives details about each snapshot ID, parent, commit, time, operation. The manifest list path, summary. Useful for investigating specific versions.
Right.
The files table shows all data files in the current snapshot path, format, record count, size, partition info, and crucially, column statistics like min-max values within that file. Super useful for understanding data layout and potential for pruning or compaction.
Ah, checking file sizes.
Exactly.
Yeah.
The manifest table describes the manifest files in the current snapshot path, size, partition spec ID when it was added. The partitions table offers summary stats for each distinct partition in the current snapshot partition values, total record count, file count. Good for seeing data distribution across partitions.
If partitions are skewed.
Precisely.
Yeah.
Then there are all data files and all manifests, which are like files and manifests, but include files from all valid snapshots, not just the current one. Good for seeing historical file usage.
Okay.
The reps table lists named references, branches, and tags their type, and the snapshot ID they point to.
So you can see your branches.
Yep. And the entries table gives a detailed file-level view per snapshot, showing which files were added, deleted, or carried over in that specific snapshot. Very granular. You can query any of these using SQL and Spark or other engines.
That's an incredible amount of detail available just through querying the metadata itself. What kind of more advanced analysis can we perform by joining these metadata tables together?
Good question. By joining these metadata tables, you can unlock even deeper levels of analysis. For instance, you could join the entries table with the history table to trace the life cycle of individual data files, when they were added, which snapshots they were part of, and when they were eventually removed or replaced.
See how long a file lived.
Exactly. You could join the files table with the partitions table to get a more granular view of file sizes within specific partitions, helping identify skew or compaction needs. By analyzing history and snapshots together, you can understand the frequency and types of operations over time useful for auditing or performance tuning. You could even track partition evolution by looking at the partitions specified in the snapshots table. Joining these tables gives you a really powerful lens into the table's internals and history. We saw an example joining entries in history to track file lifecycle.
Now let's talk about managing different versions of our data and isolating changes. Iceberg offers some interesting features in this area, like branching and tagging, similar to what developers might be used to with Git.
That's right. Iceberg brings Git-like concepts of branching and tagging directly to your data lake tables, providing powerful mechanisms for managing data evolution, testing changes in isolation, and marking important milestones.
Let's start with table branching and tagging. How do those work in the context of an Iceberg table?
Okay, table branching in Iceberg allows you to create mutable named pointers to a specific state or snapshot lineage of your table. Think of it as creating an isolated copy of your table's history where you can make changes.
Like a development branch.
Exactly. Maybe for experimenting with a new transformation, testing a quality rule, or preparing data for a new app without affecting the main or production branch. Once you're happy, you can choose to merge those changes back into the main branch.
Okay, mutable pointers. What about tags?
Tagging, on the other hand, allows you to create immutable named pointers to a specific snapshot in your table's history. Tags are typically used to mark important points in time, like a software release or the data set used for a specific compliance report.
The immutable pointers for fixed points in time.
Precisely. Because tags are immutable, they provide a stable reference point to a past state. You might use Spark SQL's alter table, create branch or create tag commands, and then query using @branch or @tag.
That sounds incredibly powerful for managing different data versions and isolating changes. You also mentioned catalog-level versioning with Nessie. How does that extend these capabilities?
Right. Catalog-level versioning, as implemented by projects like Nessie, takes the core ideas of branching and tagging and applies them to the entire data catalog rather than just individual tables.
The whole catalog, wow.
Yeah. This means you can create branches and tags that represent consistent states across multiple Iceberg tables and potentially other data assets managed by Nessie. Nessie introduces concepts like commits, merges, and references at the catalog level, giving you a truly Git-like experience for managing your entire data lake environment.
So atomic changes across multiple tables become easier.
Much easier. You can make changes to several tables on a Nessie branch, then commit them all together as one atomic unit. You configure Spark to use the Nessie catalog, and then use Nessie-specific SQL extensions or commands to create branches, switch refs, commit, and merge.
That sounds incredibly powerful for coordinating changes across related data sets.
Hmm.
And you mentioned multi-table transactions. How does Iceberg handle the need for atomic changes that might span across several tables?
Well, Iceberg itself provides ACID at the individual table level. Achieving true atomicity across multiple independent Iceberg tables typically requires coordination at a higher level. As we just discussed, using a catalog like Nessie, which provides catalog-level versioning and transaction capabilities, is one powerful approach. Nessie lets you group changes to multiple tables in a single atomic commit.
Right. Nessie handles it. What if you don't have Nessie?
For systems without native multi-table support, you'd need to implement coordination logic in your application or processing framework. This might involve techniques like writing changes to staging tables first and then atomically swapping them with production tables once all parts are successful, perhaps using table renames or view swaps. It's more complex manually.
Okay, so Nessie simplifies that a lot.
It does. We saw a conceptual example using Nessie where inventory updates and assembly logging happened within a single transaction block with commit or abort logic.
And finally, a critical aspect of data management is being able to recover from mistakes. How does version rollback work in Iceberg and at the catalog level?
Iceberg provides several ways to roll back a table to a previous state. At the table level, you can use system procedures or commands like rollback to snapshot to revert to a specific snapshot ID.
Go back to snapshot 123.
Exactly. Or rollback to timestamp to go back to the state at a particular time. You can even set current snapshot directly in some cases, though rollback procedures are usually safer. There's also cherry pick snapshot, which applies the changes from one specific snapshot onto the current state, which is more like reapplying a change.
Lots of options at the table level. What about the catalog?
If you're using a versioning catalog like Nessie, you can perform rollback operations at the entire catalog level. This allows you to reset a specific branch to a previous commit, effectively reverting the state of multiple tables simultaneously back to that commit's point in time.
Wow, roll back the whole environment.
Yep. You can also create a new branch from a historical commit, allowing you to explore a past state without affecting the current main branch. These rollback capabilities are incredibly important for quickly recovering from data loading errors, bad transformations, or any situation where you need to revert to a known good state. Spark SQL often exposes these via xllsystem.rollback procedures or Nessie-specific commands.
That's a fantastic overview of the versioning and rollback capabilities. Now let's shift gears and talk about how Apache Iceberg integrates with streaming data, a crucial aspect for many modern data pipelines.
Indeed. Iceberg is increasingly becoming a key component in modern streaming data architectures. There are several common patterns, like direct ingestion, where real-time data flows directly into Iceberg tables, Lambda architectures that combine real-time stream processing with batch processing, where Iceberg can be the storage for both, and Kappa architectures that aim to process everything through a streaming pipeline, with Iceberg again providing robust storage.
Okay.
For our drone example, this could involve directly ingesting telemetry from flying drones, sensor readings from assembly robots, or real-time quality metrics into Iceberg tables as the data arrives.
What are some of the primary technologies used to stream data into and out of Iceberg tables?
Apache Spark structured streaming is a very popular choice for streaming into Iceberg. It offers powerful features like exactly once processing guarantees, handles schema evolution gracefully, and processes data in microbatches or continuously.
Spark streaming is a big one.
Definitely. You can easily configure Spark streaming jobs to read from sources like Kafka or Kinesis and write into Iceberg tables using append mode, often just by specifying .format Iceberg in the write stream options.
And reading streams from Iceberg.
Yes, you can also read changes from an Iceberg table as a stream, which is useful for things like real-time monitoring or triggering downstream actions based on data updates in Iceberg.
Okay. What about other engines? Flink.
Apache Flink also has excellent native integration with Iceberg. Flink is known for its low latency, stateful stream processing, robust event time support, and high throughput, making it well suited for demanding real-time applications writing to Iceberg, including support for upserts.
Good for low latency needs.
Exactly. For a more direct Kafka integration, the Iceberg Kafka Sync connector allows streaming directly from Kafka topics into Iceberg tables without needing intermediate Spark or Flink jobs.
A dedicated connector.
Yep. And in the AWS cloud, services like AWS Kinesis Data Firehose and AWS Glue Streaming ETL can also be configured to deliver streaming data into S3 buckets managed by Iceberg tables.
So lots of integration options.
Plenty. We saw code snippets illustrating Spark streaming from Kafka to Iceberg, Flink doing upserts from Kafka, Kafka Connect config, and even an AWS glue streaming ETL example.
What are some of the crucial performance considerations we need to keep in mind when dealing with streaming workloads and Iceberg?
Performance with streaming is key. The small files problem can be more pronounced with frequent streaming writes, so it's essential to configure your streaming engine and Iceberg write settings to aim for larger file sizes.
Batch up the writes more.
Kind of, yeah.
Hmm.
Adjusting trigger intervals in Spark or checkpoint intervals in Flink can help create larger batches, and you can set target file sizes in Iceberg's write options. Regular compaction of your streaming Iceberg tables is often necessary to merge these smaller files for better read performance later.
Keep compacting.
Definitely. Choosing an appropriate partitioning strategy, often time-based, like by day or hour for streaming data, is crucial for partition pruning when you query it. The write.distribution mode table property can often be set to none for simple append-only streaming to avoid unnecessary shuffling during writes. And finally, be mindful of the commit frequency.
How often you commit the stream writes.
Right. More frequent commits mean lower latency and fresher data, but also more metadata operations and potentially more small files initially. You need to find a balance based on your needs for freshness versus writer-read performance.
The classic trade-off.
Always.
Now let's talk about the critical aspects of data governance and security when using Apache Iceberg, especially when dealing with potentially sensitive drone manufacturing data.
Right, security. With Iceberg, it's really a multifaceted approach encompassing security at different layers: storage level security, semantic layer governance, and catalog level security. This layered approach ensures comprehensive protection.
Storage semantic catalog. Okay, let's start with storage level security. How can we secure the underlying data where the Iceberg tables reside?
Storage level security is about controlling who has access to the actual data files in your data lake, the Parquet files, manifests, etc.
On HDFS or S3, for example.
Exactly. For HDFS, this involves things like Kerberos for authentication, setting file directory permissions, POSX or ACLs, and maybe HDFS encryption zones.
Standard HDFS security.
Right. In cloud object storage, like AWS 3, you'd use bucket policies and IAM policies to define who can do what actions on buckets and objects. You can also enable server-side encryption, SSE, to protect data at rest.
S3 policies and encryption. Got it.
Similar mechanisms exist for Azure Data Lake Storage, using ACLs, and Google Cloud Storage, using IAM. The key is ensuring only authorized users and services can read or write the underlying files. We saw conceptual examples of S3 policies and enabling SSE via Spark write options.
What about semantic layer governance? How does that help secure our drone data?
Semantic layer governance involves creating abstracted, business-friendly views of your data. This could be through data virtualization platforms or by defining secure views directly in your query engine, like Spark SQL.
So users query the view, not the raw table.
Often, yes. By providing access to these curated views, you can enforce more granular control. For example, create a view on drone quality data showing only aggregate defect rates, hiding sensitive details. You grant permissions on the view.
Okay.
Some tools also offer row-level security, where users only see rows they're authorized for, and column-level security or masking to hide specific fields. We saw a PySpark example creating an aggregate view to hide details.
And finally, how does catalog-level security play a role in protecting our Iceberg metadata and tables?
Catalog-level security focuses on controlling who can discover, access, and manage the metadata of your Iceberg tables, who can create, drop, alter tables, or even just see that a table exists.
Securing the blueprint itself.
Exactly, because the metadata controls access to the data. Different catalogs offer different features. Nessie, for instance, provides fine-grained access control on branches, tags, and tables within its managed catalog.
Okay.
AWS Lake Formation is another powerful service, providing centralized governance for data lakes on S3, including Iceberg tables in the Glue catalog. Lake Formation lets you define granular permissions on databases, tables, even columns, often using a tag-based access control system, LF tags.
Tag-based access control. Interesting.
Yeah, you can tag tables or columns, like sensitive.hi, and then grant permissions based on those tags, ensuring consistent policies across the lakehouse. We saw conceptual Python examples for managing permissions in Nessie and Lake Formation.
So a multi-layered approach is really key to securing our data lakehouse. Finally, let's discuss the practical steps involved in migrating to Apache Iceberg from existing data platforms.
Right, migration. It requires careful planning and considering several factors about your current drone data setup. You need to assess the scale and complexity, your tolerance for downtime, tooling compatibility, and performance expectations.
Need to plan it out.
Definitely. And it's highly recommended to benchmark query performance on your current system, and then on a representative sample, migrate it to Iceberg to validate the benefits before going all in. We saw a conceptual Python script for doing just that kind of benchmarking against Hive versus Iceberg.
What are some of the common strategies organizations adopt when migrating to Iceberg?
There are several common strategies. An in-place migration involves directly converting existing data files and registering them with Iceberg. This can be simpler sometimes, but potentially riskier if something goes wrong. A shadow migration is often preferred. You set up a parallel Iceberg environment, copy data gradually, validate, and then cut over. Less risky, allows for testing.
Dual running for a while.
Exactly. You might also be migrating from specific formats like Hive tables, Delta Lake, or Hootie, and there are often specific tools or procedures for those, like Spark's Convert to Delta, though that's for Delta. Similar concepts might exist for Iceberg editions. In some cases, you might use Iceberg to manage existing raw files without rewriting them immediately, just layering Iceberg's metadata on top. And the migration is often a good time to perform data transformations, cleaning, or optimizations as you move the data.
What are the typical steps involved when migrating from a traditional Hive table to Iceberg?
Migrating from Hive usually involves several steps. First, set up and configure your chosen Iceberg catalog, like Glue or Nessie. Then, create the new Iceberg tables with the desired schema, partitioning, and properties.
Define the target tables.
Right. The next crucial step is copying the data from Hive to Iceberg. This is often done using Spark or Flink reading from Hive, writing to Iceberg, usually as Parquet. This data copy can be the most time-consuming part.
The heavy lifting.
Yeah. Once the data is copied and verified, you update downstream applications, pipelines, and queries to point to the new Iceberg tables. Finally, after thorough testing, you can decommission the old Hive tables.
This has been an incredibly insightful deep dive into Apache Iceberg. It's clear that it offers a modern and powerful approach to managing and analyzing large-scale data.
Absolutely. So as you can see, Apache Iceberg offers a really powerful and versatile foundation for modern data lakehouses. It addresses many of the challenges we saw with traditional data warehouses and basic data lakes.
Yeah.
From its robust architecture and performance optimizations to its advanced features for governance, security, and that seamless integration with streaming, it's really a game changer for organizations like our drone manufacturer example.
We hope this deep dive has provided you with a clear understanding of the core concepts and capabilities of Apache Iceberg. It's definitely a space that's moving fast, isn't it?
Oh, absolutely. There's always more to explore from, even more advanced optimization techniques, the nuances between different catalog implementations, to the really exciting possibilities unlocked by things like catalog-level versioning and multi-table transactions.
So much potential there.
Definitely. What aspects of Iceberg sparked your curiosity the most? Maybe it was the performance benefits of Z-ordering for those complex analytical queries, or the flexibility of hidden partitioning that just makes life easier for users.
Or maybe the implications of catalog-level versioning for managing the whole data lake-like code.
Exactly. We encourage everyone listening to delve deeper into these areas based on your specific interests and needs. The world of data management is constantly evolving, and understanding technologies like Apache Iceberg is pretty crucial for staying ahead. Thanks for joining us on this deep dive.
Thanks, everyone.